walls of pressure and crosswinds. The resulting aerodynamic forces are violently nonlinear. To the sky, an aircraft is a rigid mass navigating 6 degrees of freedom. It pitches, rolls, and yaws through a fluid environment that resists perfect balance. For engineers, physical chaos becomes calculable geometry. The thrashing of turbulent flight is isolated and tracked as oscillating points along mathematical axes. This pilot feel, whether an aircraft is stable or twitchy, corresponds to a precise engineering metric, the exact amount of time the system's differential equations take to return to equilibrium. High-speed flight requires translating these raw atmospheric physics into the language of regulated control theory. This regulation of physics is codified in what the industry calls handling qualities. To build a compliant aircraft, engineers must adhere to strict regulatory frameworks like MIL F8785C, which specify exactly how an airframe is legally allowed to behave. This table shows the precise numerical bounds used to categorize aircraft Dutch roll performance. Regulators sort an airframe's behavior into distinct levels, level 1 for acceptable handling, down to a dangerous level 3. Notice the strict limits assigned to the minimum damping ratio. To prove an aircraft actually meets these limits, engineers must mathematically isolate its specific second-order dynamic modes, the natural, rhythmic ways the airframe oscillates when a gust of wind knocks it off balance. The engineering objective is to tune 2 specific variables, the natural frequency of the oscillation and its damping ratio. The structure must be designed so that these numbers naturally land inside the boundaries of Level 1 certification. But physical shape alone is rarely enough. If the aerodynamic design fails to meet these handling levels naturally, engineers must design active, artificial control systems to manipulate the physics of flight. Analyzing all 6 degrees of freedom simultaneously creates a chaotic web of coupled, nonlinear equations. Trying to use that raw math for linear control design is practically impossible. To make the system tractable, engineers apply a mathematical tool called small disturbance theory. By assuming the aircraft is only making minor deviations from steady, level flight, they can smooth the chaotic variables into linear approximations. This theory cleanly bifurcates the complex equations of motion into 2 entirely independent matrices, the longitudinal and the lateral-directional. The longitudinal matrix governs motion strictly in the vertical plane. It isolates variations in forward speed, pitching the nose up or down, and plunging vertically through the air. The lateral-directional matrix handles the rest. It models the highly complex, coupled interaction of rolling around the x-axis, yawing the nose left to right, and side-to-side slipping. By mathematically decoupling these motions, engineers secure the clean baseline they need to systematically isolate and correct dangerous flight characteristics before a prototype is ever built. Within that longitudinal matrix, the first behavior engineers analyze is the long-period motion, known as the phugoid mode. The phugoid mode is a slow, sweeping interchange of kinetic and potential energy. Over the course of a few minutes, the aircraft gradually trades its airspeed for altitude, climbs, stalls slightly, and then dives to regain that speed. Because this frequency is so low and the cycle so long, human pilots easily anticipate and correct the motion. As a result, the regulatory damping requirements for the phugoid mode are minimal. The immediate threat lies in its counterpart, the short-period mode. If a sharp gust hits the nose, the aircraft responds with rapid pitch oscillations that unfold in just a few seconds. This graph shows the variation of routes with damping ratio, mapping these rapid pitch oscillations directly onto the complex plane to illustrate how pole position defines stability. The undamped natural frequency of this short-period mode is heavily dependent on the aircraft's physical mass distribution and center of gravity. Move the weight backwards, and you immediately alter where these routes sit. The window for acceptable handling is incredibly narrow. To achieve a Level 1 safety rating, these routes must be safely confined to the left half plane, indicating that the oscillations will naturally damp out and decay over time. The location of these routes determines whether the airframe naturally absorbs an atmospheric impact or if the oscillations amplify until the pilot loses control authority. Shifting focus to the lateral directional equations, the math becomes significantly more hostile. Roll and yaw rarely operate in clean isolation. Take the aerodynamic reality of lateral directional coupling. When a pilot deflects the rudder to yaw the nose, the outer wing sweeps forward faster than the inner wing. That extra speed generates unequal lift, forcing the aircraft to roll simultaneously. The inverse is also guaranteed. Deflecting an aileron to initiate a roll creates high-pressure drag on the rising wing. That drag acts like an anchor, unintentionally pulling the nose in the opposite direction of the turn. This continuous crosstalk breeds the Dutch roll mode, a lightly damped, rhythmic oscillation where the aircraft simultaneously yaws and rolls, constantly out of phase with itself. The Dutch roll perfectly demonstrates why raw aerodynamic stability often falls short of regulatory safety requirements. Without intervention, this motion degrades flying qualities severely enough to require artificial correction. Deriving these handling qualities happens in stages. Static stability derivatives, like basic weathercock stiffness, are extracted early using scale models in wind tunnels by measuring surface pressure distribution. But capturing dynamic parameters requires putting physical metal under real stress. Full-scale prototype flight testing, alongside rigorous structural verification, like you see here, is mandatory. This is because scale models cannot accurately replicate structural inertia. The massive weight distribution and unsteady aerodynamics of a fully loaded airframe in motion require a one-to-one environment. Certification standards act as the final check in the engineering loop. If a prototype cannot meet these quantified levels, the final design cannot be validated for production. The classical brute force solution to lateral directional instability was physical geometry, significantly increasing the vertical tail area to add more directional stiffness. Modern aircraft like the Grumman X-29 cannot rely on oversized control surfaces. Utilizing forward-swept wings, it intentionally prioritizes extreme maneuverability over inherent aerodynamic stability. Trying to fix that instability by bolting a massive tail onto the fuselage would ruin the aircraft's supersonic drag profile and impose massive weight penalties. When physical geometry reaches its aerodynamic limits, engineers stop altering the external surface. Instead, they bypass the airframe entirely to solve the stability crisis. The definitive solution is artificial stability augmentation. Engineers use active feedback control loops to essentially trick the aircraft into behaving as if it had a larger tail. A yaw damper uses this augmented yaw moment differential equation to link aerodynamics and flight computers. Making rudder deflection proportional to yaw rate injects a mathematical gain, K1. This increases damping, forcing the Dutch roll routes into the stable region without adding drag. Modern aircraft operate through a continuous negotiation between two forces. Fluid dynamics dictate the natural modes of motion, while active control systems inject the artificial damping necessary to keep the pilot in command.